Okay, so now we look at the logical network design. We want to look at the aspects of the logical network design, like the LAN design, WAN design, and route architecture design. So for today, we are going to end there at route architecture design. Then tomorrow we can finish up on the remaining parts. Okay, so let's begin with the LAN design. Now, generally, our local area networks are Ethernet-based networks. Let me just pick something here. Okay, so our LANs are actually Ethernet-based. They're Ethernet-based, and normally we use switches, especially at the access and aggregation layer. We use either twisted pair cables for interconnection, especially between the access devices, and also between the access switch and the device, and also sometimes between the access switch and the aggregation switch. And we also use optical fiber either between the access and aggregation, or between aggregation and the core layer switch or router. The important parameters that we're supposed to consider about our local area networks, one of them is the transmission speeds. So depending on the user requirement, we can do 100, 1 gig, 10 gig, or even 40 gigs. It is technically possible right now to go up to 40 gig. We need to look at the port type. The port type for the devices, which we did in the previous chapter or subtopic. So are we going to use copper, or are we going to use optical fiber, or both? So as we know, they'll differ in terms of the transmission speeds and also the transmission distance. So optical fiber will normally do higher. So in our LAN, when we want to use more than 1 gig, then we use optical fiber. If we're doing just up to 1 gig, then we can use copper cables. Then the other thing we need to consider is we also need to consider the maximum transmission unit in our LAN. Typically, the default MTU for packets in our LAN are 1500, but certain applications such as MPLS VPNs, they might need to use what we call jumbo frames that are bigger than 1500. The other functions that we need to consider, for example, is whether we need packet power over Ethernet, PoE, whether we need to do stacking, and whether we need to do routing, and where exactly we need to do some of these things that we've mentioned there. So let's look at other things that you look at when you're looking at designing your WAN. So the commonly used topologies on a LAN. So I think I had mentioned this earlier. So between aggregation and core layer, we use the dual star topology. Between aggregation and access layer, we use the star topology. The main advantage of using the hierarchical layer is network extension and port scalability. As I said, you can actually extend your network also like this, but it is not recommended. It is not recommended. Now, generally, as I was mentioning again, between this, you can use optical fiber. You can use optical fiber because they offer higher transmission speeds. Here you can also use optical fiber. But when connecting to an end device, when connecting to end devices here to access devices, then you can simply use Ethernet. The twisted pair cables will be sufficient for that. Now, just to mention again, I mentioned of uplink and downlink. So this is what we call an uplink. This is what we call an uplink. This is a downlink, downlink, downlink. So when you talk of uplink is one that is connecting you to a higher layer. So these are uplinks, uplinks, outlinks. In regard to this switch, these are downlinks. So if you have a cable, if you have a link that is connecting you to the internet, then that is your uplink. So that's how we use those terms, uplink. Okay. So for your LAN, the other thing you're supposed to highly consider is the VLAN design. The VLAN design, a number of things you're supposed to consider. Number one, the assignment principle. So are you assigning VLANs depending on the type of service that the department is offering? For example, exams, finance. So you can do that, or location based. For example, hostel 1, hostel 2, hostel 3, or security based. So that's the first thing you're supposed to consider, and then you consider the assignment method. We know we have all this. We have actually 5, and the 6th one is a combination. So are you using protocols? Are there actually 5 in total? So are you using protocol-based IP, MAC address, or port-based VLANs, or policy-based VLANs? Then lastly, the ID allocation. We know that VLANs, the VLAN tag is a 12-bit, and that is 2 raised to power 12 will give us a maximum of 4096 VLANs. But we cannot use the first VLAN, which is the default VLAN, and the last one. So we only have around 4094 VLANs that we can use. Normally, this is not enough for many organizations. So even as you plan your VLANs, you're supposed to plan about continuity, so that, for example, if you're doing location-based assignment, then buildings that are following each other have subsequent VLAN numbers, for example, and also scalability, so that you can be able to expand your network with time. So those are some of the things that you need to consider when you are looking at the VLAN design. The other thing within a local area network that you're supposed to consider is STP. The STP protocol. We have the 3 types. By default, Huawei uses MSTP. And we know the benefits of each one of them. So once you connect a switch to another, then it uses MSTP. And one switch then will belong to one MSTP region. And all the VLANs in that switch will be mapped to instance 0. So these are things that you're supposed to understand. Also the compatibility, in case you're having devices from other vendors that are operating on STP, for example, or RSTP by default, then Huawei devices are actually backward compatible or downward compatible. So if you've enabled RSTP, then STP can be used if you have a device that is running that. If you enable MSTP, then it can switch back to RSTP or even STP. So in terms of MSTP design, you need to consider the region definition, the revision version definition, the instances definition, and also the VLAN mapping definition. So please find time and read about each of those parts so that you understand them better. Okay, so on STP again, it is important for you to take care of the position of the root bridge and the blocked ports. As we know, to affect root bridge election, we might need to change the bridge ID and the priority of each of the switches. To change which port is blocked and which one is not, we might need to change the port cost. So those are some of the adjustment methods. And we know the others which we learned at HCIA level. Now look here, if we have our aggregation layer and our access layer, then where do we block and where are we not supposed to block? So really, we normally configure the core switch to serve as the root bridge. So it actually makes sense. So the core switch will act as the root bridge. Then switches that are at the same position cannot be blocked. So these links cannot be blocked because most of the time they've actually been bundled together using Ethernet trunking to improve bandwidth. So if they're on the same level, they cannot be blocked. Now look here. At the aggregation layer, port blocking is not applicable. So we cannot block a link on the aggregation layer. So where do we block then? We need to do port blocking at the access layer. So those are some of the things that you're supposed to understand. Okay. So layer 2 network loop. Again, the working mechanism of a LAN is that we have broadcast packets that are shared within a LAN, and because we have redundancy design in our network, then we can have loops. So to prevent loops, we need to configure STP. Now, the network structure, that is what I was saying, we have redundant devices and links which cause loops. So the implementation defect of this differs from device to device. What this means is that even though STP in theory is meant to prevent loops, depending on how you've implemented your network, you may still have loops when certain things occur in your network. So in order to prevent loops from completely occurring and reduce the chance of loops occurring in your network, you might need to do the following. Number one, you can do STP optimization. For example, you can configure loop guard and root guard protection. You can configure loop guard. You can configure BPDU guard, and you can also configure access ports as edge ports. You can also use other loop prevention technologies such as SmartLink, SEP, and RRP. Please, when you get time, read about those ones. And there is a new technology that is used to prevent loops. It's called Trill. Trill is, what does it stand for? I'm forgetting. But when you get time, please also read about Trill, just to get an idea of how it works to support STP in preventing loops. So the other challenge on our LAN is security. So the other challenge is security. So layer 2 attacks, we have things such as the denial of service attacks that simply target the CPU by sending so many packets such that it cannot be able to process the legitimate packets. We also have traffic overload, which really just want to occupy the bandwidth so that other legitimate packets cannot be able to be processed on time. So, for example, the storms and the distributed denial of service. MAC address spoofing, I'm sure we've already looked at this. So it can be protected using port security. DHCP attacks, we have several, like DHCP snooping, which can still be protected by configuration. Some of these things we already did. ARP attack, which can be also dealt with by using dynamic ARP inspection. And IP spoofing, which is dealt with IP source guard as a mechanism for taking care of such like attacks. So you need to select a corresponding security mechanism for the different attacks. So this is also done during the logical network design. So let's look at this case study. So on a campus, network, access switches and aggregated switches are connected at layer 2. So we've interconnected access and aggregation switches at layer 2. So user gateways are deployed on the aggregation switches. So the gateways are on the aggregation switches, and aggregation and core switches are connected at layer 3 to isolate, in order to isolate broadcast domains. So we need to design a VLAN assignment solution for the layer 2 network. So we need to remember this scenario and where it's beginning from. So generally, it was a campus network where we have 8 DOMs. We have 8 DOMs. Now, each DOM has 6 floors. Each floor has 4 units. Each unit has 5 rooms. And we were actually going further in that I think each room was accommodating, I think, about 20-something students. I think each room was doing about something like that. I cannot remember very well. So how then would we design a VLAN assignment solution for this particular network? Do we create 8 VLANs, a VLAN for each DOM? Do we create 6 times 8 VLANs so that we have a VLAN for every floor? Is that sufficient? Or do we create 4 times 6 times 8 so that we have a VLAN for each unit? Or do we create 5 times 4 times 6 times 8 so that we have a VLAN for each room? Remember, when creating VLANs, we want to our main purpose we want to isolate and reduce the broadcast domain. We want to isolate. So how do you think we should create the VLANs? Per room or per unit or per floor or per dorm? For example, if each room is accommodating, let's say 28 students, or even let's say each room is accommodating 6 students, how do you think, how best, let's say every room is accommodating 6 students. Do we create per room or per unit or per floor or per dorm? Okay, so the appropriate is either per room or per unit. The thing is, we are supposed to keep the size of the VLAN. We're supposed to keep it so that it's not so big. So that is very, very important. Now, the other thing that is mentioned here, for example, is the VLAN assignment method. The VLAN assignment method. So, for example, for easy scalability and management, if, for example, we need 100, if we are creating VLANs per unit, we might need, or per room, we might need 120 VLANs, for example. So there are going to be so many. So how do we label these VLANs? Do we begin from VLAN 2 all the way to VLAN 121? So one way in which you can do it is that you use this format. So VLAN floor number, then the unit number. So if we are creating per DOM, then the DOM number. So for example, if we have 8 DOMs and we are creating a VLAN for DOM 2, then it will start with a 2, and we are creating for the 4th floor. So 4, then oh sorry, I will have started with the floor number. So you can start with the floor number. I think starting with the DOM might be better. Let's say we are starting with the DOM. I'm not following this. So we are doing it for DOM 2, floor number 4, unit number 1, like that. So that will be 241, meaning for the next unit in that DOM, it will be 242. For the next unit, the VLAN will be 243. The last one for that unit, it's going to be 244 because they have 4 units. So something like that. So you really don't have to begin from 1 going up. You can also use this kind of location-based VLAN naming. Okay, so let's look at any questions, by the way, on LAN design before we go to one. Okay, let's look at one design. So the characteristics of a wide area network: number 1, wide coverage range, high leasing costs, and complex operation and maintenance. Now, generally, it is one links that connect us to the internet. Now, normally, we cannot lay out a cable all the way from our enterprise to the ISP's geographical location, because this is not cost effective. So most of the time we use list links, which are provided by carriers such as Liquid Telecom, for example, in Kenya. And you have to pay monthly rental fees for those list links. So that's why we're saying they're high costs. And complex operation and maintenance, because you don't own it, so you have to involve them in case you want anything done for you. Okay, so let's move on. So these are some of the technologies that you can take advantage of when it comes to list lines. So one of them is called SDH, or synchronous digital hierarchy. Synchronous digital hierarchy, SDH, uses what we call time division, TDM, time division multiplexing, to share a single line between multiple people. Time division multiplexing. On the other hand, OTN, or optical transport network, uses what we call WDM, or wavelength division multiplexing, to share a single line between several people. So SDH, most of the time when you're connecting via SDH, then the interface on your router that you're going to use is, for example, a POS or an Ethernet. So packet over SONET, which can offer speeds of up to about 622 megabits per second. You can also use another special interface, which is called multi-service transfer platform. Now, because of the low speeds, SDH is rarely used nowadays. One of the most commonly used ways to connect to the WAN from your enterprise is OTN, or optical transport network. As I've said, OTN uses wavelength division multiplexing. It can do speeds of up to 10 gigabits per second, and it's widely used for backbone networks interconnection. Then we also have these technologies such as ATM, frame relay, X.25, and Ethernet, which are used by packet switched networks. We learned about frame relay at some point, so they can also be used to interconnect WAN. And lastly, we have the traditional telephone networks, circuit switched networks. So you can also connect to your WAN via those traditional telephone lines, like what we call the public switched telephone network, or integrated service, a digital network. So again, for these ones, the speeds are quite low and they are rarely used. So those are some of the technologies that you can use for WAN interconnection. So the layer 2 protocols that are used to interconnect you via the WAN, When you're using POS, DDN, or E1, then normally it's a point-to-point connection, and the protocols you can configure is HDLC or PPP. When you're using the traditional telephone lines, interconnection is point-to-point. You can only be able to use PPP protocol. When you're using optical transport network, then P2P again, the protocol is Ethernet here. Then when you're using public switch network, you can configure point to multi-point, like what we did when we learned frame relay. So you can use frame relay, X.25, asynchronous transmission mode, ATM, or Ethernet. So generally, point-to-point links are the ones that are used for WANs, and the protocol that is commonly used is PPP. And OTNs provide Ethernet access services. So this is the most deployed, widely used is OTN. Now, with traditional networks, as we have seen in the previous slides, we were leasing lines through those technologies that we've just looked at. The advantage of leasing lines is that the bandwidth is guaranteed. The disadvantage is that it's expensive. Another advantage is that we can do quality of service, high reliability, high security for leasing lines. But nowadays, to connect to the wide area network, we use the public network to connect to the over the public network. We use a virtual private network. Now, with virtual private network, you don't have a guaranteed bandwidth because it's shared, but it's very cost effective because you don't pay for any lines, or you only have to pay for the configuration of the VPN. But quality of service is not guaranteed. It also has poor reliability, but because it encrypts the packet, then it also offers high security. So most of the time in current networks, we choose or we prefer VPN over leased lines because especially of cost. Now, access network technologies. Now, there's what we call a last mile access. Now, the last mile access is actually the network between the user network and the backbone network. If I can give you a good example, I have Wi-Fi at my house, which is offered by Safaricom. So that interconnection between Safaricom's backbone network, they have a termination point somewhere, and my connection at my house, that is what we call the last mile access. So last mile access, it enables communication between the user network and the carrier's backbone network. So my network and Safaricom's network. Now, there are several technologies that can be used to implement last mile connection. One of them is what we call the Digital Subscriber Alliance, DSL. This uses telephone cables, and it can have asymmetric uplink and downlink bandwidths. So we have symmetric and asymmetric. Asymmetric means different. So for example, if the maximum bandwidth is 10 megabits per second, it means I can upload. Normally the downlink is higher, but you can request your service provider depending on your usage. But asymmetric means I can upload, for example, at 7 megabits per second, but I can only download at 5 megabits per second. So the uplink and the downlink bandwidth are different. So that's what we call asymmetric. Then you must have heard of FTTH, or fiber to the home. So it can be FTTH, it can be FTTO. So this X here simply means it can be H, O, and any other thing. So fiber to the home, fiber to the office, fiber to the campus, fiber to anywhere else. So with this, normally it uses either twisted pair, and it has high user density, and you see the speeds can get up to 1 gigabit per second. Then we have passive optical network. So this one uses pure optical fibers up to the termination point. Like right now, Safaricom is installing fibers at people's houses. So that's a good example of passive optical network, because the fiber is getting up to the termination point, up to your house. So it's no longer the future, it's actually current, and it can offer very high bandwidth. The other examples of last. Okay, hello, can you hear me? I think I lost my internet connection. Okay, so I think I was here on wireless. Is that so?
Yes.
Good. So on wireless, for last mile access, we can either set up a Wi-Fi connection, or we can use LTE. So the 4G network, for example. So again, this is already happening, and it can offer speeds up to 100 megabits per second. So when you get time, also read about HFC and asynchronous dialing. Okay, let's move on. So let's look at a case study. So remember, we are still referring to the same campus network that we've been talking about from the beginning. So a campus network needs to connect to an education network on which access points are deployed in the same city. So the straight line distance between the two networks is about 10 kilometers. So it is estimated that the bandwidth requires about 1 gigabit per second. So what one link technologies can be used? So which one link technology can give us 1 gigabit per second and span over 10 kilometers? Hmm? Okay, so you need to consider the cost and the availability of that particular link within your area. So generally, the optical transport network can offer such speeds, and of course fiber can also be able to span such distances. Otherwise, you can also use a VPN to connect to your ISP. So those are the two cases that we have. So let's now look at the other logical network design, which is the last one you're looking at, route architecture design. So route architecture design is concerned with IP address design. How do you design, you logically design your IP addresses? So let's begin by looking at the rules for allocating IP addresses. The rule number one should be uniqueness. So an IP address, of course, has to be unique on the entire network. Number two, you need to ensure high efficiency by designing a proper mask length. Some of the common mask length that are used is /32. Normally, this is called a host route because it's used to identify a device. So to uniquely identify that particular device. So a certain IP address /32. Then we also have /30. Of course, /30 will give us how many addresses? Just two addresses, assignable addresses. Because 2 raised to power 2, we get 4. We can't use the first and the last, so we only have two addresses. So for that purpose, it's normally used when you want to do point-to-point connection, point-to-point connections between devices. So we used a /30 so that we have two assignable addresses. Then, other than using the classful addresses, we know that it is recommended for efficient use of IP addresses, it is recommended that we use variable length subnet mask. And I think during the IP addressing topic at HCIA, we covered this concept and how to do that extensively. Okay, now the other things that you're supposed to consider, for example, is aggregation. Aggregation, we know that if you have several subnetworks, you want to ensure continuity, that is consecutive addresses of adjacent network segments, so that they can be aggregated into a single IP address. When they are aggregated, then they save the device resources such as memory, so that your routing table is not going to be so long. I'm sure we still remember what aggregation is. So you need to ensure continuity. So if you ensure continuity, then aggregation is going to fall in place automatically. Again, scalability. So you need to reserve addresses for expansion. So while you're choosing a certain IP addressing scheme, you need to consider scalability. And lastly, we have manageability. So manageability is how do you, for example, assign those particular addresses to the end devices. So IP configuration methods, we know that you can either do that manually or through a protocol called DHCP, which is also called dynamic allocation. This one used for network device configuration. It is simple, but the configuration workload is heavy. DHCP, we all know it, used on clients, and multiple security mechanisms can be used together because it opens another Pandora's box. It is susceptible to certain attacks, but if you implement DHCP snooping, dynamic ARP inspection, and IP source guard, then it can be able to cater for those security threats that face this particular protocol. So the other concept that you need to be aware of is the routing boundary identification. Routing boundary identification. Now, as we know, we have layer 2 devices and layer 3 devices. Generally, we've mentioned severally that at layer 3, at the core layer, we use layer 3 devices. At the aggregation layer, we use layer 3 devices. At the access layer, we use the layer 2 devices. However, that does not stop you from using a layer 3 device at the access layer. You can still use it. But what is the routing boundary, and why do you want to create that particular routing boundary? Some of the things to consider is the device cost. Generally, layer 3 devices are more expensive than layer 2 devices. You also need to consider the bandwidth cost. You need to consider security challenges and also maintainability. Because, for example, if all these access switches are layer 3 devices, it means that managing that network is going to be more strenuous, because you have to manually configure all these switches with an IP address. Maybe you're going to have different VLANs and so on and so forth. So those are some of the things that you should consider. Okay, so let's look at this. So client gateways, when client gateways are deployed at the aggregation layer, then the access switches work in switching mode. That means that the access switches only do switching. They forward data based on layer 2, and the devices above the aggregation layer work in routing mode. What that means is this. It means that here we're working on routing mode, while here we are working on switching mode. We are working at layer 2 here, but at the top we're working at layer 3. On the other hand, when client gateways are deployed at the access layer, switches on the entire network work in routing mode. So what does that mean? If the access switches are working on layer 3, are layer 3 switches and are working on layer 3 mode, then the entire network is in routing mode. So that has issues, for example, with maintainability and so on. So it really depends with what you want, but you should take cognizant of some of those factors. Then the other thing you need to consider is the routing protocols, so that you know which one to select. So routing protocols are broadly divided into 2 categories: interior gateway and exterior gateway protocols. These ones are used within an autonomous system or a single domain. This one is used to interconnect different autonomous systems. So some of the common protocols that are used within enterprises, either OSPF or ISIS, both of them use link state algorithm. OSPF is hierarchical, meaning we divide into areas. It forwards based on the bandwidth cost. It is fast in terms of convergence, and it is a loop free. The same applies to ISIS. Then BGP, interdomain routing, strong bearing and manipulation capabilities because of the BGP attributes, and loop free. Now, in practice, OSPF is preferred in enterprise networks, while ISIS is preferred for carrier backbone networks, so for ISPs. BGP for interdomain routes, MPLS and BGP VPN networks. Static routes are commonly used in scenarios where there is no redundant connection. So if you don't have a redundant connection, then you might need to configure a static route. Now let's look at some of the problems with, for example, the OSPF, with the OSPF design. Now, as we know, OSPF has a hierarchical design in that we normally configure area 0, then expand from there to have area 1 and other areas. The tradition is that you configure the core layer as area 0, because that is where the core layer and aggregation layer should be in area 0, because that is where all the other extension of your network is going to stem from. Now, let's look at this one, for example. This example, we are focusing here. Now, when everything is working correctly, then the network is going to work okay. Yeah? But if we have a link fault, for example, in the backbone area, these may cause the area to split. These may cause the area to split, and therefore we might have routing problems. Remember, all other areas have to communicate via area 0. So for example, if we have a link fault there, then we might have a problem with the communication. Now the next one is this one here. And the problem is the suboptimal route. So what is happening here is we know that with OSPF, intra-area traffic is preferred over inter-area traffic. So if this device needs to send a packet to this device, it's going to send it to the ABR here. Then the ABR is not going to send it outside this area. It's simply going to send it, for example, to this guy because it's connected to this guy but not this guy. Then this is going to send it to this one, then this one to this one. So the reason as to why we are saying that is a suboptimal route is because the easier way, for example, will be this. You see, if we have this interconnection, then the easier way will be we just send it there, then it is sent here. Or we sent it here and it is sent here. So just two hops instead of going through, just one hop instead of going through two hops as we are having here. So that is a suboptimal domain. So as you design your logical topology, you should take into account such considerations, OSPF design considerations, so that you can avoid such problems. Okay, so we have a scenario here on routing protocols. So routing protocols need to be deployed on the campus network to function as route bearers. So the question is, which routing protocols do we want to select? Then what is the boundary between layer 3 routing network and layer 2 switching network? And what is the routing protocol design? So as we've said, for a campus network, for example, it will be ideal to use OSPF as the IGP. The boundary between layer 3 routing network is between the core and the aggregation layer. Layer 2 switching implemented between the access and aggregation layer. And the routing protocol design should consider some of the flaws of the OSPF, network design, such that when problems occur, then areas can be isolated, or when problems occur at a particular point, then we might also have suboptimal routes. So those are some of the things that should be considered. The next one here is also a case study on the IP address allocation. So IP address allocation solution. Remember, we had like 8 dormitories. So we have the network segment 10.0.0.0/8, and it is recommended due to the scale of the campus network. So if the education network segment are specified, use the corresponding ones. So in this case, network segments are divided based on the principle of 1 room per VLAN. Remember, we said we are giving each room a VLAN. So again, you need to consider the building number, the floor, the unit, the room. So by doing this, you need to find out the number of users per room. So depending on the number of users, then that will determine the mask. So for example, here, if it is /29, how many addresses do we have? So 29, 32 minus 29. We have 2 raised to power. Is it 3? So we get 6 minus 2, we get 4. I think this will give us 4 addresses. 4 addresses per room. So maybe we have 4 people in each room.